Hello everyone, my name is Yifan. In this video, I'm going to be presenting our paper, Efficient Parallel Determinacy Race Detection for Structured Features. So in task parallel code, programmers use provided language constructs to express the logical parallelism of the programs. In particular, the use of feature provides a flexible way to express parallelism. Feature parallelism can be expressed using create and get. For example, we use create here to indicate that fib n-1 can run in parallel with the continuation. In addition, it returns a feature handle to this task. Later, we can call get on this handle to enforce that the program has to wait until this task finishes. Task parallelism means a wide range of parallel program needs, but there are still pitfalls programs need to be careful with. One of the challenges we focus on is determinacy race. A determinacy race occurs when two logical parallel instructions access the same memory location and at least one of them is right. Determinacy race can lead to non-deterministic results, and therefore they are often bugs. For example, in this task parallel code, we have two parallel strands, strand 1 and strand 2, and they write different values to the same variable x. Then in the main function, we output the value of x. Since strand 1 and strand 2 run in parallel, the output value can vary depending on the scheduling order. Such bugs are hard to debug because determinacy races do not necessarily produce wrong results in every single execution. So to ease the job of debugging determinacy race, people proposed on-the-fly race detector. Here, on-the-fly means the race detector runs during the execution of the task parallel programs and checks if the program has a race. It can provide strong correctness guarantee. For a given input, the tool reports a race if and only if the program has a race. And ideally, we would like a race detector that detects the race efficiently. So a couple of work have been done on race detecting the task parallel programs using features. This table lists the best known results of race detection algorithm targeting programmers that use features in different fashions, namely general features and structural features. I will define general and structural features later in this talk. So in particular, the state-of-the-art sequential algorithm for race detecting general features takes order of W plus K square time to construct necessary data structure for race check, and each check can be done in constant time. Here, W is the total work of the parallel computation, and K is the number of future operations. In comparison, the state-of-the-art parallel algorithm for general feature has the same construction time, and each check now incurs more overhead, log k hat. Here, k hat is the number of future operations within a single future task. However, the high overhead of the parallel algorithm can be offset by the scalability that it gains in practice. Now we look at the prior work for the structured features. The state-of-the-art sequential algorithm for structured feature achieves a nearly optimal execution time bound. As we can see, the use of structured features allows for more efficient race detection algorithm, at least for the sequential algorithm. So in this work, we explore a parallel algorithm for structured features that achieves better execution time compared to the parallel algorithm designed for a general feature. In our work, we propose SF order, a provably efficient parallel race detection algorithm for programs with structured features. Let's put our result back to the previous table. As we can see, our algorithm is able to bring down the query overhead to constant time compared to the parallel algorithm for general features. Although our algorithm incurs more construction overhead compared to the sequential algorithm for structured features, the high overhead can be offset by the scalability our algorithm gains in practice. Our experimental result also demonstrates that when compared to the sequential algorithm for structured feature, our algorithm beats the sequential algorithm as long as the program is executed on 2 cores or more. We also compare SF order against the state-of-the-art parallel algorithm for general feature. The results indicate that our algorithm outperformed the state-of-the-art parallel algorithm designed for general feature as well. So before I dive into the detail of our work, let me first go over some necessary background. So first, the execution of a task parallel program can be modeled as a directed acyclic graph, or DAG for short, where node represents strings, which is a sequence of instructions without parallel constructs, and edges represent dependencies among strings. As the task parallel program executes, the corresponding DAG unfolds dynamically, meaning that a node gets reviewed only after executing all its predecessor nodes. In task parallelism, the computation can be categorized into different classes based on how people construct the computation. We first look at fork-join parallelism, which is a traditional parallelism paradigm. A fork-join program can be expressed using keywords bound and sync, and the execution of such programs generates series parallel DAG, or SPDAG for short. A SPDAG has very nice structural properties that enable efficient risk detection algorithms. In comparison, the use of features provides a more flexible way to express the parallel computation compared to fork-join. The use of features can be categorized into 2 classes: general use of features and structured use of features. General use of feature has no restriction on the use of features, and each feature task in the program may contain fork-join parallelism, and therefore the execution of a feature task can be modeled as its own SPDAG. Then the entire program that uses a feature can be modeled by a set of such SPDAGs and a set of arbitrary additional edges representing the dependencies arise from the use of general features. And the NSPDAG no longer has the nice structure properties, which makes developing efficient risk detection algorithm difficult. In contrast, in structured features, we can only call get on each feature handle once, and there is no resist on the feature handle. And such restrictions grants additional structural properties to the corresponding DAG. Here we refer to such DAG as structured feature DAG, or SF DAG for short. Now we look into on-the-fly risk detector in more detail. A risk detector typically has 2 components. There is a reachability component that tells us whether 2 strands are in parallel. Here, if we consider the DAG model, then 2 strands are in parallel if there's no path from one to another. For example, nodes U and V in the DAG are logically in parallel because there's no path from one to another. The other component is access history. It tells us which strand accessed a given memory location before. Now let's do a quick example to see how these 2 components work together to find a determinacy rate. Say both node U and V perform write operations to a shared variable. Now consider a parallel execution of this DAG. Say we first execute the left branch, then we go back to the right branch. Now we execute node V. We first query access histories and learn that node U has also accessed the same memory location. Then we run a reachability query on U and V. Since there's no path between them, then the result of the query is that U and V are in parallel. Therefore, we find a race. In risk detection, reachability is always the most important and challenging part. Now we look at the intuition of how our algorithm handled the reachability for SF DAG. We consider node U in feature F and node V in feature G. We want to check if U and V are in parallel, or in other words, if or not there's a path between them. We first consider the case that U and V are in the same future. Then to determine if U and V are in parallel, we only need to check if there's a SP path between them. Here, SP path means that the path does not contain any edges arising from executing create or get. For general future, this is not sufficient. As we can see in this example, even though U and V are in the same future and there is no SP path between them, U is still sequentially before V because there exists a non-SP path between them. Now we move on to the case that U and V are in different futures. In this case, to see if U and V are in parallel, we do two checks. First, we check if there is a path from the last node of F to node B. If so, then U must be sequentially before V because every single node in F has a path to last node of F, and therefore has a path to V. If there's no such path, then we check if there is a create path between them. Here, create path means that the path does not contain any edges arising from executing get. Again, these two checks are not sufficient for general futures. As we can see in this example, U and V are in different futures, and there isn't a path from the last node of F to V or a create path from U to V. But there exists some other path that doesn't fit into any cases. So in our work, we design different data structures so that we can run those checks efficiently. Due to the time limit of the talk, I won't dive into that, and you can find more detail in our paper. We have also evaluated our algorithm in practice. We compared our algorithm SF order against the state-of-the-art sequential algorithm for structured future and the parallel algorithm for general future across 5 different benchmarks. This bar chart shows the sequential running time comparison among the baseline, the state-of-the-art sequential algorithm for structured future, the state-of-the-art parallel algorithm for general futures, and our algorithm. As we can see, our algorithm incurs less overhead compared to the parallel algorithm, but higher overhead compared to the sequential algorithm on single core execution. And this figure reviews the parallel execution time on 20 cores. As we can see, both our algorithm and the state-of-the-art parallel algorithm for general future beat the sequential algorithm in parallel setting. And our algorithm performs better than the parallel algorithm for general future. To sum up, in this work, we exploit the particular structural properties of SFDAG and propose an efficient parallel risk detection algorithm for programs with structured futures. And empirical results indicate our algorithm outperformed both the state-of-the-art sequential algorithm for structured future and the state-of-the-art parallel algorithm for general future.